everybody. I hope everyone's doing good.
Hello, Sanchin. How are you?
Hello, sir. I've been very nice, and I hope everyone had a great day. And we're just waiting for a couple of moments before we kick off with the webinar. And I really hope from everyone to please have some patience by the time we wait for the rest of the attendees. And let's enjoy some introductory videos till then.
Hello, my name is Kehinde Adeyemi, a practicing civil and structural engineer based in Abuja, Nigeria, with near 15 years wealth of practice experience that cuts across simple residential to complex multi-story commercial buildings and infrastructures while consulting for leading global brands like KD Prime and Arab. I am your instructor for this course, and I would be training you on the use of Protastructure 2022, which is a powerful, future-forward, and building information modeling compliant tool for structural engineers. Protastructure 2022 is an intelligent program and a complete software tool that is a 4-in-1 suite for the structural analysis and design of buildings and associated infrastructure. In this course, we will jointly explore 3 of these suites, which are Protastructure, the modeling, analysis, and design environment, Protadetails, the powerful suite for detailing and construction drawings documentation, including schedule and quantities preparation, and Protabeam, which allows for project and model interoperability with other BIM tools such as Autodesk Revit. As you journey through this learning experience, you would grow your structural, analytical, and design skills as we thoroughly explore all the components of the structural design of simple residential to complex multi-story buildings. You would learn the principles of modeling structural members such as solid, flat, ribbed and waffle slabs, slant columns and shear walls, pad, raft, pile foundations, and you would also comfortably learn how to carry out static analysis using yield line methods and finite element methods of load decomposition. You would learn how to implement interactive designs and optimize outputs to prioritize safety, ensure economy, while maintaining the aesthetics of your design requirements. Furthermore, you will get to explore design macros for the analysis and design of structural engineering features such as double arm, spiral, and load-bearing staircases, different shapes of swimming pools, cantilever retaining walls, scaffold designs, and associated calculation and reports documentation for all these processes. To aid your learning experience, we have provided some model files for your reference as you journey along. I am already excited about this in-depth learning experience for you, and I look forward to meeting you in class.
So welcome everyone once again. Okay, so I think now it's fine. I heartily welcome you all and thank you for taking out your precious time and joining to our webinar. So now here we begin. And before our respected speaker takes up the stage, I'd like you all to go through a PPT with me, and that will basically describe about our company and also about slightly our techniques of conducting the training approaches, our webinars, and also a little bit about our today's topic. So let me share my screen with my PPT. So the topic for today's webinar is structural modeling and design of inclined reinforced concrete members using Protastructure, right? So Naziza Global, as you have already come to know, it's an online training platform Nextly, so now I think we can come up to today's webinar. And as you already know, we would like to know a little bit about our respected instructor, sir. He is Kehinde Idiami. He's a multiple award-winning professional engineer, and he holds a master's degree in structural engineering. He began his career as a civil engineer in 2011 and is currently working as a civil and structural engineering project advisor at the British multinational professional services company ARUP. From here on, I'd like to give the stage to our speaker, and from here on, he begins. Thank you.
Very well. Thank you, Session. Please, am I audible?
Yes, sir, you are audible.
Yes.
Very well. Thank you. Thank you all for your time on the session. Thank you for making it here. So I will just permit me to share my screen in a second, but just to throw some more light on what Sashan had shared. I'm very delighted to be driving this session, and I'd first of all like to thank Inziza Global for the opportunity, and also to appreciate them for the opportunity to also deliver a course. I mean, pretty much two courses. We have about the Protastructure course is now available. And so I'm just trying to share my screen. Just a second, please. Can anyone see the screen yet? It seems we have someone's hands up. Not sure if it's a response to it.
Yes, we can see the screen. Yeah, I can proceed.
Okay, very well. Thank you. I think it will be very helpful since it's a webinar. It will be very helpful to have feedbacks. I think that will help me to know if I'm on track or not. And so to get started, I'm glad that you can see the model on the screen. Just to start with the fact that if you are a part of our trainings so far on Protastructure 2022, I'm sure that you would have experienced the creation of this model that you see on the screen. In that training, we took the participants through the processes of creating models like this and being able to implement some aspect of the model, for example, like the slant columns that we can see on this screen. So just to start with, we are focusing on slant members, structural members, with focus on reinforced concrete members in this webinar. And certainly, we have members that are both vertical, and we also have members that are both horizontal with respect to their placements. Members like columns, like walls, shear walls, all fall in the category of vertical members for reinforced concrete. And members like slabs and beams, of course, we know that these are all horizontal members. And so with a software like Protastructure, and as a structural engineer, you discover that you have multiple options to be able to create slant columns, slant vertical members, walls. You can also have slant slabs created. And what I'll be focusing on in this webinar is just to show you how you can accomplish some of this. And so without much ado, I'd like to ask though, Sashan, are the participants to respond interactively to me on this in this session? Or I'd like to know this so that I know if we can be a bit interactive. For example, I'd like to know if anyone here has had experiences using Protastructure so far. I'd also like to know if the audience has some good grasp of the software to let me know how detailed or to what level of technicality I need to get to. Sashan, if you're there, or anyone, please. Thank you. Are the participants able to interact, or I have to just go on and then we take maybe questions and feedbacks afterwards?
Yes, I'm here. Hello?
Yeah, Session. I was asking, right?
Yes, sir.
Just to kickstart the webinar, I'd like to know if if there are participants that have a good grasp, that have experienced the Protastructure environment before, and that can relate with what we're able to do, so that it can be very engaging and interactive. I'd just like to
Okay,
maybe
okay.
have some quick feedbacks from the participants. Thank you.
Okay,
So
okay.
maybe anyone can share their experiences if they've been exposed to the software that we're looking at today, Protastructure 2022.
Yeah, sure. If anyone wants to share, I think the chat box is open to everybody for now. You're free to type and share your experiences.
Very well, very well. All right then. So I'll move on. So what I'll do I'll make a simplified demonstration of how we can move through the processes of creating slant structural members. And so to get started, we can create a new project. And to do that, you can go to the icon right there and click on new project. Let's save these changes, and then we can select a project code and also provide a name, a reasonable name for the tool, for the model that we're creating. And so let's say this is webinar on slant columns. And so then it's important to select a code, the type of design code that you intend to utilize to guide your design. And so in my case, let's say that we are selecting, let's say let's say UK BS 8110 or Eurocode. I think I'll prefer to go with Eurocode, since we are now seeing a shift from the BS code to the Eurocode. And so once selected, you have your work environment. And from there, you can define your grid system depending on your reference grid system. Sometimes we might need to model closely to an architectural model. I won't be doing that in this case. And so we will generate a simple grid system. Say we have something like that, and we can generate a series of grid lines for this purpose. And so let's say that we have grid lines at 5 meters by 5 meters interval. And then we have, let's say, 1000 millimeters and 1000 millimeters, and say 500. And then we have about the same grid system on the other hand, in the other direction. And then we can OK. And so we have this system of grids created on the screen. And then, so for columns, of course, columns are vertical members, as I had highlighted earlier. For the purpose of this demonstration, I will create, say, I'll create two other floors, say, just two other floors like that. And then I'll add that. So I have just two floors for this model. And so let's get to the ground floor level. So let's say that we are going to create a column, a few columns at, let's say, the intersections, the intersecting coordinates right there. And so we can have, we can define those column properties, the size, the width. Let me work with, say, 300 by 300. And we can place those columns just like that. And so let's now say we had beams intersecting them, but we're trying to create, say, two levels of slant columns with, let's say we're going to have a slant column at this point, right? And then we're also going sitting on the cantilever. And then we also have that in the other direction. And so what I'll do is to, just for us to appreciate this better, I will, sorry. So I will Let me try to split my screen right there. Let's have two views so that we can have a vertical view and a plan view and a 3D view. Okay, so right here, I'm just trying to work with a very simple model. So let's say that at this floor level, we had cantilever beams sitting over those columns, and then we can get back to the modeling. Beam, let's say those beams are also about the same width with that. And then we have, say, a 500 deep beam is fine. And so let's create a first beam that way. And so what you have right here now is that we have a slight cantilever there, but the focus is to be able to say, based on the design that we have a slant column that sits right here at this point, and then also have a system where you're also able to have, say, walls, you have columns, and then also the members themselves, for example, the horizontal members also slanting as well. And so we could have a column at this point at the upper floor. So let's say that I do decide to generate this column to the upper floor. We can have that generated to the second floor. And then, so what I really am trying to do here is to showcase how we can have a slant system created. And so what I'll do is that I'll copy this column from this point. I'll copy that column properties, and then I will replicate this column at this point, right? At that point and at this point. So now, if we take a look at these three columns, we see clearly that we have a system where this obviously is vertical above this. We have this sitting just vertically above that cantilever end there. However, this column here currently does not have any kind of support. And so it's possible that at the upper level, that we have a system where we have a column that is totally off the support but needs to be supported by a member such as a beam. And so what this tool, Protastructure, allows us to be able to do then is that we can redefine the support for a member like this by slanting it all the way to whatever point we intend to have that slanted to. And so I could right click and get to the properties where I can see the properties dialog for this member. And right there, I have the options that allow me to define under the properties of this column. You have options that allows you, first of all, to either define a change in elevation for that member, irrespective of other members present. So I can redefine the height of this member, and I could redefine the depth. However, under the general section, you can see here that we have a section that allows you to define, or to redefine rather, the bottom insertion point of a vertical member like this. And so for this member, where we see the property, we can utilize the bottom insertion point right here, and we can come to the plan view, and we can click on that plan view. And right here, you see that initially the bottom level, the bottom point of this column was at C5, grid line C5. But right now, you can see that the bottom right now on this panel is now C4. That's this particular point here. However, we can't see that yet. So until I then click on update before you are able to see and appreciate how that column now has a support. Now, if I go back to the first floor level, I might not be able again to see on plan immediately what is happening here. But if we go to a tool such as if you go to the review section and you activated the visual interrogation, from there, you are able to immediately see that you have options that allows you to see what is happening from an upper level to a bottom level. So in a case like this, where you have a transfer column, which is slant, of course, we can then activate that we would like to see how this column appears on the member below that, which is a transfer column, of course. And so from there, we can clearly see that we've not only created a column that is now slanting from a grid line at an upper level, but this column is also likewise, excuse me, please, it's also likewise clearly shown that it is being supported by this cantilever, picked up by this cantilever at that point right there. So this is one very practical example. We can see that the process of creating this slant member, for example, is pretty simple and straightforward. And this is one of the fantastic features of Protastructure, because it allows you to visually and easily create complex members. Of course, it starts with something as simple as this, but then as you proceed, you discover that the process of modeling and creating members like this are quite simple, and they are very user-friendly. And this is one very important aspect of the tool. So let us again create another system of cantilever beam here. And in this particular case, let us assume that we have a system where we also have a similar beam column like this. However, we have a system where this is slanting backward inside. So, what we worked on earlier was that we had a column that was out and that was now slanting back in, right, based on the support. But what if you wanted to have it done the other way around? So it's more of how you go about creating your model, more of a modeling approach. And so in this case, let's jump back to story 2, and let's say that at this particular level, okay, sorry, I'm still there, I'm on the 3D view. So let's jump here, and let's say that we wanted to create a similar column like this. And then this time around, let's have that column, say, placed somewhere here. And then you now want this to, say, slant backward into the system, into the other grid line as we had. So this slanted outward, and we want this to slant backward. Again, this is just to show different methods of being able to create a slant. So for columns, really, the process of doing that is simply redefining your bottom placement position. And this allows you to either model in the right place and redefine that bottom position, or define the top position and then reorient the final position of that bottom level. So in this case, I've placed the column at grid line intersection B5, but say that, again, we want to slant this back inward. And so what we can do, based on what I've modeled here, rather, what you need to do is to place the column, define the actual point of the top position, and then you can redefine the bottom position. So I'll take this off temporarily, and then reactivate the properties of this, and then we can now redefine that bottom position. Once you redefine that, you can see that that has changed, and then again you can update, and then you see how quite straightforward that process is. So now let us see how this may differ for creating walls. And so let's get back to the second floor, right? To the first floor, sorry. And then at this floor, let us see how this process is a bit different for creating walls, because for columns, you can define columns by a single grid line intersection, but walls obviously are defined by their path along either a grid or along a line, right? And so let's get to the modeling section here, and let's activate a wall. I'll work with the 250 setup as is, and then we can define a wall at this point, start point and end point. So depending on how you create your structural members, for example, you would have a start point and an end point, and this is very important for structural members such as walls. For this wall, for example, you see that the way we created this, we started from this point and we ended at that point. So technically, your start point is the I point and your end point is the J point. We'll see the importance of this in a short while. So if I activated, if I returned to the properties of this wall, as you can see right here, I can see that this wall has a top section, and you can see the I and the J right there. And then you can see the bottom as well. You can see the I point, that's the start point, and the J point. So essentially, the top and the bottom of this column of this wall is located on the same grid line. And we can see that the top is defined, the start point of the top is defined by grid line A intersection 6. And that is obviously where we started from. You can see grid line A right there, and you can see that intersection 6. So we started from there, A6, and we stopped there, B6. And so if we are to create a slant or translate this wall into a slant, then how do we go about that? Again, it's about the same process, only that this, in this case, it's almost a two-step, right? So we have the I point and then we have the J point. And so we could utilize this, right? And click on the button selection. Sorry, I lost that properties. And so we could redefine that point, right? By then returning to select what grid line, the exact grid line that we intend this to align with for the bottom. So once I click on grid line 5, you see how this differs a bit from how we created the column. For the column, we were dealing with a particular point. For the wall, however, we are dealing with 2 points essentially. And so I could then redefine this as well and click on that to redefine the bottom point. And then once I click on update, again, we can see how this has been slanted, albeit gently, but we see that that slant has been achieved right there as well. So why am I going through this? First of all, to let you understand that the process of creating slant members, such as columns and walls, are quite very straightforward in Protastructure. And again, it's very visually appealing and also allows the engineer to be able to carry out multiple checks while at it, right? And so let's then go into framing this whole system up and then maybe doing having something to review horizontal members and how, again, we can go about creating these slant members. So I'll activate again the property of this, and I can create those members that way and that way and this way. So this time around, I have this beam framing into that wall. We now have this framing into that wall, right? And then we can as well now have, we could redefine this member to frame into that wall, but let's see, let's add an additional member here. Okay, so now let's take a look briefly at beams while we look at advancing this model. Let's take a look at this beam, for example, or rather, let me move over to this very end here. There are instances, depending on the size of your cantilever, there are instances where you might want to have an upward incline of the cantilever beam so that it can help to assist with deflection or deflection or the additional loads, if any, that are coming on that. And so managing such a system obviously would require that you are able to have some slants in that beam. So for this beam, let's say that instead of having this cantilever beam straight as is, since it's a cantilever, obviously, we intend to have, let's say, a section of that beam at the cantilever end slant upward, or depending on the design. For example, there are instances where you might want to design a gallery as a cantilever beam. And so in that instance, you might have a situation where the beam is slanting downwards. But let's take a look at this beam. And let's activate the property of that. And now we can see the property of that member there. And what I wanted to highlight to you again is that within the 3D section of each member like this, you have the opportunity to be able to redefine the elevation, the 3D elevation of the start end or the end or the closing end of that member. So for this member, we have started creating from this point and we moved that way. And so the point where we started it from is the I end, and then the point where we ended it so far is the J point. And so say that an engineer decides that he needs to have an offset somewhere around there to a certain value, let's say to about 500. You can have this and you can have that updated, and you can see how this beam now slants upward. And this is a very useful design method or approach, right, for members such as beams that are cantilever to help you deal with cantilever deflections that would be excessive. So once it's slanted up, again, that kind of helps to reduce the expected deflection and the sagging probably over time. And so again, this is one method as shown, and this is one capability of the tool, giving its robustness to allow us to create slant members. I'm just trying to demonstrate a couple of slant members as we go on, just to get us started on the course. So now let us see. Let us take a look at an alternative way of having this slant. So let's say that you intend to have a slant downwards instead. Again, it's about the same method. So looking at this, we have this slanted upwards. We can have this slanted downwards as well. But again, you have to place some importance in learning or knowing how you have modeled the structural member. So if, for example, I mistakenly, this is the I end, obviously, that's the point where it joins with the column right there. So let's say that I accidentally input a value for del I here, and say that I have this as 500. Again, you can see how that takes that off of that joint. And so it's very important to know exactly what you intend to do regarding your model. If you create that model yourself, you should also have some good grasp on the, you should be able to have some good grasp on the nomenclature or the naming methodology around the solution or the software. So let's return this to 0. And in this case, we want the J end to sag, to incline downwards, right? We can have this specified as a negative value. And so this is one very important aspect of Protastructure because it is sign responsive. So that means that if you specify, even from activities such as offsetting grid lines, it's very important to know that a positive value is quite different from a negative value. So in this case, given the coordinate, you can see the Cartesian coordinate right there. You can see the Z direction, which is the positive direction. So if you want this to go up, obviously you need to align that with the positive direction of that coordinate system. And if you want it to go to be inclined downwards, again, it's about the same process. And so for this minus 500, I would expect that when I update that beam is inclined downwards, as you can see right here. So we have a system where we have one inclined and the other downwards. And we have been able to achieve this so far by interacting in a very friendly environment, both in the 3D and in the 2D with these members that we have created. So let's move on then to looking at a very simple instance of where you can have, you can drop levels, because sometimes when we refer to inclined members, it might not also be the incline, but it might also be that you intend to achieve certain drops with some members. And so let's look at where we have a slab within this system, and we intend to modify that slab to slant appropriately. Just a random example now. So let's create a slab within this system right here. Of course, you need to define a load case if you are going to create a slab, because these are primary members for receiving loads. And so let's quickly create some loads. I'll use the load generator, and I'll just quickly generate some load in there. And then now I have the slab properties dialog open. So let's set this to say 175, provide a few loads. Let's provide a few loads here. Say this 2, and for dead load, let's say this 0.5. And then we can create that slab as is. Now, the first thing is to let us know that there is an additional tool as well that is available within Protastructure. So apart from being able to interact with the members using their 3D geometric definitions, we can also have access to an additional tool within the modeling tab that is called plane definition. And what this plane definition does is that it allows you to be able to define levels using a plane. And then based on that, you can migrate members that are within the perimeter or that are within the framework of that plane to be relocated based on the plane definition that you've provided. So let's create a plane. In this case, you can see that within the status bar region, we are asked to select a beam region or define an insertion point. Of course, you can always have access to that insertion point definition here. You can modify that depending on what you're working on. So you have an axis region, a beam region. I'll leave this to a beam region because we obviously have well-defined beams for this example. And so let me click on that area there, and I have actually placed a plane there. Now for the properties of this plane, you can see that right here within this dialog box. And so before I continue, I'd like to emphasize that, again, another very useful aspect of being able to use Protastructure to accomplish tasks like creating inclined members is that you would always have an interactive dialog box that helps to give you a visual presentation or representation of exactly what you're trying to do. So if you look closely, if I zoom closely at this plane right here, plane member right here, I can see that 3 points, 3 geometric points are being defined. So we have point number 1, we have point number 2 as well, and then we have point number 3, right? And all those 3 geometric points have been captured within this dialog box. So technically what this is saying is that with the use or with the aid of these 3 points, I could define levels, and then those levels can then redefine how the structural members within that region behave and how they act. So let's say that we have points let's say point number 1 here. We intend that this axis remains, we intend that this axis at this point, that we intend that this axis remains at a 0. And then that's with the relative level where we are right now. And then we decide that we would like to have this point raised up along this perimeter by, let's say, about 750 millimeters. And so what we then need to do is to search for that point, which is point 1 in this case, right? And we can provide that elevation there of 750. And then we can update that. So once we update that, what we see right now is that this level here has been updated to 750 as we had defined. However, we see that points 2 and point 0 and points 3 rather are still at 0, which of course is what we anticipate. But then the plane has been defined, but this has not, the members have not been requested or been instructed to align themselves with how that plane has been created. So to do that, you can select that plane. You can select that plane. And by the way, for every member that you create within the structure tree area, you have such members listed. So I could have achieved a selection from this point right here. And I could also achieve a selection through the structure tree, as you can see right there. And then you could right click. And then when you right click, you can see that within the fly out on screen interactive menu there, you can see that there's an option that says move members to plane. So once you define the plane, you can then use this plane to govern how members within how members interacting with that plane then behave or respond based on instructions that you're giving to that plane member. And so for this, I can then specify that members should be moved to that plane, and we can see that prompt on the screen letting us know that this would affect all the members that are within the plane definition. And so once I click on yes, you can then see how we have this slant right here. So this has literally affected all the members that have been defined within this section for this particular plane. So again, we see how we can easily achieve using a plane member. You see how you can then achieve a slant slab, and also not just a slant slab. You see how the whole section right there has also been modified to amend itself or to adjust itself to the plane that we define. Interestingly, there are always instances where you might want to have members that are not exactly responding to that inclination. For example, let's take a look at this member here. What if you do not want this beam to be inclined, but you intend that this slab should be inclined, maybe serving as a roof, some kind of roof, and then you can then have block wall in between this beam right here and then that. That is very possible. Even for the columns that you have here, you could redefine the elevations of those. And what I would like to show you now is to see how a member like a plane insertion has affected this, and how we can also maybe make some tweaks to that if to allow us with some flexibility on the model. And so let's select this beam, for example, and get back to the properties dialog for that beam. If you switch over to the 3D view, you can see that the modification to the eye end of the beam, which of course you can see right there on the screen, has been defined by that plane. Initially, when we were looking at the creation of these two beams right here, we didn't use a plane to create these slants or this inclination. However, we went directly to the 3D section and we modified them, and we had our slants. But in this case, we used a plane to define that, and based on the definition provided by that plane, it automatically updated the geometrical features of these beams based on the elevation or the Z factors of input that we had made for this particular area here. And so let us then go back to this. Recall that we were saying, what if you do not want this to be governed by the activities of that plane? And so you could come back here, right here to this section, and then you could cancel the effects, right, of that plane. So what I'm doing is that I'm saying, no, I do not want this plane to determine how this beam behaves. And based on that, we see that the modifications to the elevations have been corrected back to 0. And once you click on update for that particular beam, you see how this then goes back to the level where it was before. And then pretty much about the same process. This is what you have again for other members. You could redefine that for this, you could redefine that for that. And then this allows that level of flexibility that the engineer would always want. It's very important that an engineer or a design professional is able to stay on top of his structural designs. You want to be sure that you are in control of what you are giving or what you're doing.
Hello?
Yes, hello.
Excuse me, sir. I think we'd like to pause for a couple of more minutes, and we'd like to take the questions, if any, till whatever we have come along this far with the software. So I think we can wait for a couple of minutes and let people ask if they have any queries before we further proceed.
That's fantastic. That's fantastic. Thank you. Please, if there are any questions, please, we can have that. Thank you.
Yeah, so I request all the attendees, in case you want to ask any question, if you want, you can either ask it directly in the meeting chat, or else please raise your hand and I'll give you the mic access if you want to speak. So there are both options. So please put up your queries. Okay, for the question that Samuel has put up on how will we get the recorded video, so I assure you, you will not have to worry about that. The webinar is being recorded and you will be getting the link to the recorded webinar via your email addresses. So that won't be an issue. Also, there is a question, and the question goes like, in Africa, normally we have a ground supported slab when designing the column. How do we take it into account the fixing provided by the bottom ground supported slab? So I hope the question is clear. If not, you can also speak up.
So if I understand the question very well, this question speaks to a ground supported slab, right? So I want to assume that is a raft slab. If this person can clarify that question, are you referring to a raft slab? If you're referring to a ground supported slab, maybe you mean a slab on grade. And so if this is your question, if this is what you intend, it's very important to know that at the foundation level, within Protastructure, once you model your structural members, if adequately modeled, you'd find out or you discover that if you go to check during the design, rather, at the point of design, or even at the point of modeling, you are able to clearly see that the connection to that system, to that slab system, is rigid. In other words, that's a moment transferring a connection right there. And within the Protastructure module as well, you have the capability to redefine the connection or the connectivity of these structural members, especially for horizontal members like beams. You can redefine how they're connected. You can redefine if they have a rigid connection or if they are to be treated as a simple connection. And for columns, however, you discover that for columns and walls, especially at the foundation level, referring to your question, most of these connections, especially within concrete members, are treated as rigid, even at that foundation level. Okay.
Okay,
Okay, yeah. So he clarified that question. Sorry, let me look at the chat box section. Just a second. Okay, so what I mean is we normally have pad foundations after backfilling the ground, correct? We normally cast a 150 millimeter ground slab for the ground floor. Therefore, what I wanted to know is how do we determine the fixity provided by it? Okay, so
also, in case you want to share your screen is not visible right now.
yes, so I will share my screen, but I'm not exactly, just a second. Let me share screen. Okay, please do let me know if you can see the screen. So your question,
Yes,
so that question makes us to jump a little bit ahead, but I have to mention here that within Protastructure, you the slab on grade is not a structural member, except if it is a raft slab that you're trying to design. And in that case, that raft slab is going to be located as directly on top of the subgrade, which then acts as a load-bearing member. And so you don't expect that a non-structural member will give significant. As a matter of fact, you need to, which is the line that Protastructure has taken, because that member is not a structural member. It is sitting on the backfill, and that member is simply to primarily to demarcate between the grade and the living area or the finished level, or to create a transition between, of course, the natural ground and also the interior areas of the building. So it's not a structural member. And so Protastructure essentially ignores that because, first of all, it's not load bearing. Secondly, it does not significantly contribute to the strength of any of the structural members. And so it is not primarily considered in design. So what I mean is this, right? Let's say just for a second, just to be able to provide a very reasonable response to what this question is and to make that very practical. Let's take a look within this 3D let us take a look at the ground foundation level, right? So if you take a look at that foundation level, you see that what you see here at story 00 is the level that we've defined where you will arguably have your slab on grade, right? Or rather your ground slab, right? Which is non-structural as I defined. However, the depth here, which again, you can see that we have an expression that obviously shows that the support here is rigid. You have moments in all three directions to be transferred to whatever member you have here. And you also see that it's going to be a fixed type of connection. That's the icon that you can see right here. So the point I'm trying to make here is that for that member, for the ground slab that you're referring to, again, it is non-structural. Because of that, this does not contribute significantly to the design requirements of any of these structural members. So essentially, Protastructure ignores that. However, if you go back to the stories section within the structure tree and you decided to look at the edit story feature, you can see that you have a foundation depth that has been defined here. And so if I'm creating any member that is now a structural member and that is acting as a foundation member, for example, is going to be placed at this actual depth, which is at this point right here. So this would obviously then affect the support rigidity and the fixity of the whole building as it affects stability, right? However, for the ground slab level, that is ignored within this program. I hope I've responded to your question.
Yes, sir. And we also do have one more question. The question is, how do we cater for the staircase loading and modeling?
How do you achieve staircase loading and modeling? Okay, so that's well understood. So I'll just do a quick model just to demonstrate this. I think it's a very fantastic question. And this is one question that comes up a lot during use of Protastructure. And so let me cancel this for now and let's return to our model. And so let's say that for this particular model, that we do have a system. Let's say that for this model, we do have a system that tries to convey users, right? From let's say we want to create a ramp, right? Let's say we want to create a staircase essentially from this point, right? From this grid line 3 all the way to grid line 2 right here. We want to achieve something like this. One of the easiest ways to achieve that is by using the plane members as I defined earlier, and at the same time combined with the structural loads that have been anticipated or calculated for your staircase. So we know that staircases would have a waist. They would also have the steps themselves. So you expect that for the dead load, for example, you have the dead load from the weight of that staircase. You also have the dead load from the steps themselves. So a very good approach, for example, to solving that is to convert those triangular steps, because by the time you subtract the waist of the staircase from that, what you have is that you have a series of triangular loads, right, that are now sitting on the staircase. So a very good approach is to decompose or to translate those triangular steps, to translate them into rectangular systems and add that load as an additional load on the slant slab. So what I'm trying to say essentially is, for example, let's first of all create let's create a slant slab somewhere here. And so to do that, what I will do is that I will define a slant slab within this area just for the purpose of quickly demonstrating a response to this. And so let's see that I will create a slab, and in this case let's say that the waist of that staircase were 200 thick, and as a 200 thick staircase, waist of 200. You then have the triangular loads of the steps, as I mentioned. Let's say that we're able to translate this into an additional thickness of about 200 based on area conversion, area and volumetric conversion. You're able to convert that step load into an additional thick area of 50 millimeters over that slab. And so that gives us a total of about 250 millimeters thick slab, right? And then for this particular member, let's say that we want to define this by axis region. And so I'm going to hold down control right here from my end, click like that. So this is just to make a very quick demonstration, right? For this particular question that has been for the particular question that has been asked. I could change the support system of this to one way that way, and then so that I know that this staircase, for example, is spanning between a support here on the ground and then spanning all the way supported by that cantilever beam there. So I think this is one very important aspect of your design when you're modeling staircases, because what we had earlier was that we had this showing this staircase, this slab as a type 1 slab. And so what it did was that based on the yield line method of load distribution, it's wrongly going to transfer this load, and you will have errors by the time you are going to have discrepancies when you transfer the load eventually for your analysis. So let's say that we have the support partly on the ground and then partly on this beam. Then I'm going to change the orientation to a one-way so that I know that it is spanning in between, which is a very typical scenario that we have for staircases. And then based on this, I could then create a plane member. I could create a plane over this, and then I'll now use that plane to create that slant. But to quickly answer your question first, it's important to go back then to the properties of this slab. If it's going to be treated as a staircase based on our expectations, we can go to the properties, and within the load section, you would, of course, have been able to know what live load or dead load that you're designing for. So for the imposed load, if I go into that imposed load, I can see a pre-populated list of based on codes that I'm using, and I can easily select any type of load that suits my configuration here. So let's say that these were for some kind of bedroom in hotels and motels, or let's say maybe a hospital ward area. I think ramps are very common in hospital wards, so we can have that as a 2 kilonewton per meter squared load. And then for the dead load, we can then redefine any additional load that you have. Take note that the self weight has been captured already. And so what you will be looking for is any additional load, for example, tile finishes, screening finishes, POP, maybe on top, below the staircase. You'll be looking for additional loads such as maybe, depending on whatever it is, maybe your finishing material, it could be marble, it could be porcelain tiles. The weights of these materials are different. And so it's important for you to understand that load per square meter. And so let's say that we have an additional load of, let's say, 2 kilonewton per square meter on this particular slab that I intend to model as a staircase, right? So in Protastructure, what you are able to do essentially is that you can model the ramp as is. Maybe in future releases, we will be able to model the actual staircase for design. But as it is now, what you can model is a ramp to represent your staircase. And this is very logical and acceptable in the sense that a staircase essentially is a slanting slab, right? That is spanning between two directions. And so this allows us to be able to treat it that way. And then back to the loading, you can update that load to ensure that that load is captured within that slab. And then for that inclination for the staircase, what we can then do is to utilize the plane tool right there. And then again, we'll create that plane over this member. I'm still going to use the axis region, hold on my control. I can use a different method anyway. Let's say we decide to use the pick axis method. I could select the axis that bounds that area where I'm interested in. So I've clicked on grid line C, and you can see that listed there. I'll click on the next one, either in a clockwise or anti-clockwise manner. You can see two there. and then I click on the next intersecting grid member, which is F, and then I can come back here, click, and then click the last one. And then so once you return to the point where you started, you can see that that plane member has been created over that. So what I can then do is to look at the points of this plane. We are currently at the first floor level. And again, before I continue, let's take a quick look. You can see that the story is 3 meters high, right? And we are currently at the first floor level. So that means this first floor level is reference 0. And so if I'm going to create this slant, I need to drop this level right here, which is the Z 0.3. I need to drop that to -3 meters to take me to the ground slab level. Yeah. So what I then will do is to right click, activate the properties dialog if it's not activated. Mine is, and so I look for 0.3 right there, and I can specify -3,000 right here. And so that drops this slab all the way to the ground slab level. And then once I do that, I can click on update. But remember that this slab is not going to move an inch until you instruct it that it should be defined by the geometry of the plane, right? So going back there, I can then right click and say move members to plane. And once I click yes, I can now see that this member here has been moved, right, in line with what I would have expected. But this is not correct because I'd imputed this value in at point 3, right? And so what you have here is that you have 0.3 here, you have 0.1 here, you have you have 0.2 here. So what I could do is to either redefine how I intend this to be positioned such that I have that slant in the direction I want it, which is this way. So I want this beam to support this, right? I want this beam to be able to support this slab here. And then I want this point to then be slanted all the way down. So what you can do in this case is that you can redefine each of these points in order to achieve your expected outcome. I mean, what you just see happen now is something that usually, if you are not very careful to define your points, especially on a very complex model, you can discover that you are having a lot of rework and you are having a lot of time lost, right? So I will undo that. And then what I'll do this time around is that I will go back to the plane definition. And then based on this plane definition, I'm going to change the orientation of this point 3. I will change this to this point here. And then I'll leave only point. I could then leave this 0.2 here. So let's get back to that, the properties for that. Okay, so using first of all, let me change this of data. And so using the point property right here, using this 0.2 right here, you can redefine any of that points. So for this 0.3, I want to relocate 0.3 to this point right here. So what I can do is to click on that, and then I can click on this point, and then I can update. So you can see that 0.3 is now here, and then I have 0.1 here, and then I have 0.2 here. This gives me more control over how this will now behave. And so in this case, I could then relocate 0.2, let's say to this point right here. So let's try that out. 0.2, we can click on that icon, click right here, and then update that. And so now I have 0.2 here. So this allows me to easily define 0.3 along this line as both remaining on 0, while this point along this line can drop. So this time around, we now go back to 0.2 and define -3,000, and then we can update that. Then once updated, we can then return and ask that we move members to the plane. And then we see that although this beam has dropped, the slab has not dropped. So what we can then do again is to look at, we can look at how, let's see the properties of that. Let's check the type Okay, the type is proper as expected. So let's see. I think what we're having really is that the slab is not fully captured within that plane. And so I'll just tweak this a little bit just to have more control. Just a second, let me do this. Properties. I like also have more control over this. So let me just undo that. Okay, right now. So that is now updated based on what this was supposed to be. So you can see now that we have this slab, we have the slab slanting. We also have the column, however, dropping with that. But again, like I showed you earlier, you have a lot of flexibility over how these structural members behave. So let's say that for this particular beam and this column, that we don't intend them to slant at all. We can get to their properties. And based on that property, you can see that the JN here is dropped to 3 meters. So you can update that, and then you can also update that, and that returns that beam to the level as expected. And then we can return as well to this column, go to the properties of that column, get to the properties of that column. And sorry, I'm not sure. It seems I'm selecting multiple members at once. Let's see. So sorry, I'm not able to see that. Let's see, let's check that from here. Okay, so properties of that column, and when you look at the 3D view, you can see that again, this has been dropped by 3 meters based on the actions of that plane. We can set this back to 0. 0 in this case is not 0 as per the ground level. This is 0 relative to the position or the level where we place the plane, right? We place that plane at story 1. And so obviously at that level, because you had placed that plane at that level, that is the reference level, and that is the 0 level in this case, right? So I could then update this back, and then what you have now is that you can see that we have a column and this system as is, but we have a ramp, right? So this is obviously displayed as a ramp, but because we have already included the thickness, we have transcribed the concrete steps into an additional layer of rectangular thickness over this. We've captured that in the self width, increasing the thickness from 200 to 250. And then we had also loaded this appropriately. I can then arguably let you know that I can design this. And then once I design this, irrespective of whatever other method I use to design that staircase, which obviously is a slab, then my staircase has been properly and accurately captured and designed for, right? So I hope that I've been able to answer your question based on this. Is this clear enough, or is there any other question at this point?
So you could check the chat box. There is
Okay,
one, I
very
guess.
well. Sorry, because I'm sharing my screen, it's a bit difficult for me to cycle in between the chat box and also. All right, so let's see. Please, how will we get the recorded video? Okay, please, you can get to the team. I'm sure they're recording it. You'll be able to access this at a later time, depending on, of course, on terms and conditions. Okay.
So it's the last question. You can scroll down the question.
Yes.
That is by pace. It was.
Yes, I can see that
question.
question now. So
Yes.
another question I had was, in Prota, if we only model the columns and beams in a framed building and the wall loads we insert as line loads. Now, when we add wind loads to this structure, does the wind load only act on columns and beams only, meaning the area of columns and beams, or the wall effective structure, meaning wall length x width? If now, for example, we added the masonry walls, does Prota then consider the wall length of structure X, height of structure? Okay, so I understand your question, and I think, again, it's a very brilliant question. This is one area where, you know, when you are designing like high-rise buildings, you want to be very careful about. So there is one very clear approach that I know for this, and that I know that a lot of professionals also utilize out there. I may not be able to fully delve into this because it goes beyond the scope of this webinar. However, I can provide a very straightforward answer to you. So when you are computing, please take note of this response. When you are computing the area that is affected by the wind load or the wind force, let me put it that way, you will consider the entire area that is going to be impacted, right? But when you are applying the load, so there are two things, right? There is the computation of the load, and then there's the application of the load, right? So when you're computing the load, of course, you will take cognizance of the area that will be impacted. If you have walls there, you would have that wind acting on that wall, and then that area, the whole area that is acting on, also affects the building, right? So yes, you will need to consider the area of the wall, right? But when you are applying the load, you cannot apply wind load to masonry block walls because masonry block walls are not structural members. You are not expected to do that. What you're expected to do is to either decompose such a wind load into a point load, right? So if I had a wall area of, let's say, 5 meters by 5 meters, so let me just utilize the screen here to do that just shortly. So let's say that we had a wind force acting on this area here, and we had masonry block wall here, right? Or rather, let's make this a little bit interesting. So let's say that I generated these two columns right here. Let's say we generate this to the next floor. Sorry, I'm on foundation level. Yeah, that was why I couldn't select earlier. Sorry. Okay, so let's generate these members to story 2, for example. And yes, close. So we now have a column there. Let's also, let's say we placed a beam there as well. Let's place a beam at that point. And then let's define a wall for this area. I'm sorry, right? I just want to make this as practical as possible, but I will not go very deep into this question. Again, as I mentioned to you, it goes quite beyond the scope of this webinar. So let's go to creating a wall load for this. So let's edit loads, and you have the dialog box that then comes up. Again, as I was trying to explain earlier, so let's just provide a wall load there. Let's specify the height of this as 2,850 millimeters, just to the soffit of that beam. I will accept these load values for now, and then I'll okay. Oh, sorry, I didn't apply that. Sorry. Yeah. Okay, so let's just quickly run through that again. To 850, and then you need to click on that wall, right, to place that load. So once done, we can click on OK. Now we see the wall, that wall that has been created. You can see that wall here. So what I was trying to explain to you, right? Let's say that we have wind load acting on this surface, right? I cannot begin to load this wall with such a wind load. It doesn't make sense because it's not a structural member. And though the weight of this block wall is considered in structural design and analysis, it is not expected that this wall will receive a load. So you would have to decompose those loads either as a point load and distribute them to the joints of these structural members. That is one method. You distribute them, and you can easily select a member like this, and you can edit the loads. And based on that, you can define point loads and then define the direction that point load is going to act, right? And then you can even specify, you can be as specific as specifying the exact point within that member where that point load is going to be acting and in what direction that it is going to be acting. You see, you can specify all of that. So This is quite complex and also very interesting to do. So you can decompose that as a point load acting in the direction of the wind, or you can decompose that as a line load acting on the member through the length of the member. So I could decompose the wind load acting here and apply it directly all through on this member, or apply it on this member horizontally, or on that member, or on all of them all together, right? I think one more thing that I'd like to point out here is that it's very important to know that the joints are the most susceptible to wind loads. You want to know how your wind loads affect the joints and how it may displace those members. So many times you see this being applied as a point load directly on the joints that are affected, that are framing such a masonry block wall. Let me see if we have any other question here. Okay, it is clear. Very well. All right then. Okay, so so based on what I've shown so far with respect to the actual modeling of these slant members, does anyone have any questions so far based on that? How to create slant members? We have randomly seen how to create slant slabs, how to create slant beams. We've seen a number of methods. We've also seen how to create slant columns and walls, right? Are there any questions so far? If there are no questions, I'll proceed. I'll proceed at this point. So what I've shown so far is randomly, right? So the focus here really is not peradventure to begin to do anything complex within this webinar, but to let us understand how very flexible these tools are and available to the structural engineer, depending on the complexity of your model and depending on your requirements for the model. What you see is that you are able to create different kinds of, you have the flexibility to create different types of slanting members, and that allows you then to have more control on your model and to accurately represent what your client is looking for. So let's look again at what I created here earlier. Although this is a very simple case where I've used a thickness, a slab thickness that is not very complex, but you have instances where you could have an auditorium. You have instances where you could have an auditorium, and based on that auditorium, you have seating arrangement that are all slants, right? So that again can be modeled as a series of slant slabs, and this is very interesting, very, very interesting, because what then that does is that it allows you, again, it's a question that is very similar to what we have here. But in that case, what you're simply doing is that you are modeling you are modeling an auditorium, and you're able to model your slant slab, which is the slant seating arrangement like a theater. And this is another thing that you can do, just leveraging a tool like this. Now, in such scenario, you even have instances where the beam actually slants and follows such a member like you see here. And so again, this really allows you to be able to design complex and multiple members, right? So let's see, moving on to, let's try to give some more reasonability to what we have, and then have a system where we're able to quickly run some analysis and design and see how each of these different members perform, if there are no questions moving forward. So what I'm going to do now is that I will modify what we have here. I'll modify this model just to quickly give it some, also help us see some of the challenges we may have, because once you begin to create a complex slant members, then I can assure you that you would have to be you need to be more detailed about your approach with how you model, and you also need to be very detailed with your approach with respect to how you also carry out your analysis, because if you don't model right, for example, you are going to begin to have a lot of issues at the point of running analysis. So let us look, for example, at what we already have here. I'm going to go back to this first floor level, and I'll create a connection between this wall and this beam by either modifying this or extending this cantilever. So it's no longer cantilevered, rather it's going to be sitting on this wall. So what I'll do, let me just get back to the properties of that. I'll delete that, and then I'll just create a connection between those two right there. And so obviously this now is a transfer column that is sitting on that beam, but this time around that beam is no longer a cantilever, but we have that connection right there. And so within this space, for example, we can then place slabs. Let's get to the properties of this. I'll review this to say 175. I'll maintain the loads appropriately. I'll change this, and then I'll modify the insertion point as well as the beam region. So you can place there. Sorry. Yeah, can place that right there, and then there. Okay, and then we can also place within this region. In this case, let's place that way. So I was also sharing earlier, of course, there are other methods of placing a slab like this. So we could explore, like, say, pick points. And in this case, we can pick the actual points of the intersection where we intend to have that slab defined. And so we can have that created that way, right? Okay, so let's get back here. So for this system here, we can see clearly that, you know, this slab is showing you that it doesn't really have a support there, and then that you can see clearly as shown by what you have there, right? So of course this is very normal, but like I shared with you earlier, there are challenges that comes with creating complex members like inclining members, because you need to be certain and to be sure that you are modeling the way you need to model. This slab can actually exist like this real life, but at the point of analysis, for example, you would need to know that because there's no support here, the yield line method would not correctly transfer these loads to the column. You might need to consider some alternative methods, for example, like finite element meshing, right? So the point here is that as you create these slant members, know that your load configuration, your load distribution, your load transfer would be distorted, and you have to use the right methods, right, to complete that model, right? So let us then look at this section right here. Let us generate the other columns to the next floor, and then let us see if we can run some analysis and see the kind of outcomes that are possible with respect to what we have right now. This is a very simple model again. We are not doing anything complex other than being able to let you see how easy and you also need to be very careful with how you run your analysis to ensure that you are right with regards to what you're doing, right? So let's select these columns and generate these, for example, to the story 2. And once done, I'll close this. And I want to show you something here. Now, because sometimes when you create inclined members, like I shared with you, some other issues or challenges may come with it, and that may not be the actual case. So let's take a quick look, right? Let's take a quick look at what is happening here. We have this beam right here that was placed on story 1 at the first floor level, but because we used the plane inclination to define the new level, this jumped up, and as you can see, it will look like these columns are now directly extending beyond this first floor and then connecting themselves at this floor, redefining the top level, right, of this changing the orientation or the top level of what we had earlier. Now, this is a very, very common scenario. As interesting as it is, it could be a lot of problem. It's possible that this wasn't your intention. You probably want this beam to exist at this level, yes, but you probably want it to be connected. Let's say you want it to be connected to these columns, right? And not changing the top level of these columns here. So you probably want this column to span from the ground floor to the first floor, and then you want this column right here not to start from this point, but to start from the first floor and then just have this connect as a secondary member, right? So how do you correct scenarios like this? Let's say that was your actual intention. Again, you will need to first of all look closely at your model. It's very important. And then you can go back to the properties. For example, let's look at the column at this level. If I go to check the properties of this column, you will see that in the 3D section, you see that the bottom offsets have been provided at the bottom, and this is defined by the plane. And you can see how that has changed the orientation of this member. You can change that again by canceling that and updating. And now you see that that column drops back to the level that we expect it to drop. It also automatically however, does not affect the other column there. So I'll show you what, right? If let's say that I wasn't careful enough, right? Just to make this as practical as possible. Let's say that I wasn't careful enough to review. Let's say that I just corrected the orientation and the elevation of this column. And once I've done this, I didn't note that there was a lap here and I tried to run an analysis. What you're going to see is that you have an error in your analysis. So if I quickly jump to analysis now and click on building analysis, before running the analysis, let's do a quick building, a model check, right? And you can see all these checks can be carried out. And so once I click on start, you see that I have an error here. And if I scroll up to that error, you can see clearly this is very predictable, right? You can see these are the actual columns. You can see 1C2 and 2C6 overlapping vertically, right? And so this is one of the challenges that I mentioned, right? That if you're not careful enough, as you create changes to this model with inclined members, you discover that you might have, imagine that this were a 10-story building, just an example, and I generated this all across to those floors with this error. What happens is that I now start going floor by floor to correct that mistake. That is rework already, even at the design phase. And so again, this is why I'm emphasizing that, yes, the tool is very flexible to use, but you need to be careful and be very diligent with how you go about your model. So we can go back to the properties of this, right? And then we can go to the 3D and we can update that. And then you see that now they are no longer lapping. So I still have my slants. The model is still very correct, but this scenario is just different from the previous scenario that we saw. Both of them are correct, right? But you must ensure that you modify this model or you create your slant to meet your expectations, your design expectations. So if we go back to that building analysis now, and we carried out a model check this time around, you discover that we shouldn't have any errors anymore. You see that this is quite very straightforward. You see that that error is now gone, right? So now let's get back to the roof level, right? Let me also generate this to the upper level, story 2. And then I'll close. Okay, so what I just want to do is to go to the plan view. This. So I've created some members that I don't intend to create. So sorry about that. I will just okay, so just to give some form to the model that we are creating now. Again, you can see a repeat of that issue somewhere here. So let's just correct that. Another good thing I think with Protastructure is that when you're creating models like this, you could also use them. You can select multiple members, and when you go to the properties on the real-time interactive dialogue on your screen, you can also see how the levels of this have been modified on the screen, which from here you can also correct that. So instead of going to the properties one after the other, you could have this updated from here. So I could use the column-wise editor, for example, to update this to say 0. And I could have that corrected right from here. And once I close, I see that this is corrected, obviously, but this, because this has both the I and the Z change, we updated just one of those. So I could go back to the properties, and in the 3D section, you can see that the bottom value is still offset there. So I could set back this back to 0 here, and then, sorry. Okay, updates, and there you go. Yeah. All right. So now, at this roof level now, I know that we have been discussing creating slant structural members, but I need to also let you know that just to let us know that there are some buildings that could require that you have reinforced concrete roofs, and those roofs can also be made of slant structural members, but it's not anything different from what we have shown so far. So you can have slant beams that are reinforced concrete. We have some of these type of buildings in some parts of the country, for example, in Nigeria, where I domicile. And then you can also have roof members that are also slant, even though those may not be reinforced concrete, but you could have instances where you also have a slant roof members. So I just let you know that, again, the application goes beyond the floor levels. You could extend that to the roof levels, and you could also even have that extend to some other type of members that are not exactly structural, but maybe aesthetically pleasing. Yeah. So then, at this level, let us. I'll leave this model like this for now, right? And then I'll run a quick analysis. So the reason why I want to do this is I know that there are some issues already, but those issues are not modeling issues. Rather, they are issues with the analysis that we are going to see in a short while. You will see that if I go to story 1, like, for example, for this slant member here, which we have created, you see that the load distribution based on yield line method is not correct. And I know that already by just looking at how that load is distributed. And so we are going to have a situation where our load will not be properly accounted for. So in this case, if I decided to go to the building analysis, and so under the model options, right, under the slab model, we can see that we can have an option to include slabs in the building model where we can generate the finite element mesh. But at this point, I'm not going to do that just yet because I need to demonstrate to you that there are instances where you could have a situation where your loads are not fully accounted for. So I'm not going to check that just yet. I'm going to utilize the regular yield line method, which is load decomposition by yield line method, to carry out an analysis for this. So let's run a quick static building analysis for this. And I'll just do an analysis. I'm not going to be designing. So let's do that. So you can see, first of all, like I shared with you, you can see that we have an error that is already coming up, telling us that nodes are not in the same plane. Nodes in different planes can be an issue for you, are constrained to move together. Undesirable effect may accrue based on that diagram that you've created. Now, this was one of the points I was trying to point out, that yes, while you are trying to create your slant, because this brings more responsibility. This gives this brings more, I'd say that, attention to the processes and the methods of how you go about your model. So when you ran your building analysis earlier and you carried out the building model check, you saw that there were no errors because those errors, basically, they check your geometries, they check how you model, they check how you go about maybe placing certain structural members. But at the point of analysis, you discover that it might be quite challenging if you do not have something reasonably created, right? Or if you have not properly created your model, what you are going to find is that you have an issue where you are probably not even able to run an analysis, and then it becomes a very big problem. You may not be able to meet up with your timelines. You may be frustrated just because you're not doing things right? So now, even though I've clicked OK on that, we know that there's an error in the design, right? But it will still proceed to run the analysis. And by the time you finish running the analysis, you see that you have a feedback that says warnings have been encountered during building analysis. These warnings must be carefully checked before performing the building analysis, right? So obviously, there are issues in the model, and those issues arguably or obviously are coming from the slants that we have created. Some of these slants are not properly supported. Some of them are not properly transferring loads, right? And so what we can do now is to get to the building. We can get to the post analysis, and then one of the very quick checks that we can look out for is to try to look at the analytical model. And one of the areas you can easily know if you are running into trouble of any sort is that within the analytical model, you can easily see how these members are behaving, right? So this analytical model now, as you can see, does not capture the slab, right? This does not capture the slab. And the reason why is simply because we only had an analysis that was done based on load transfer from the slab to the beams. And so what we see at the actual frame, which is the beam, and what you also see as well is that you see how only these frame members respond to themselves. Of course, you can run through several options here to see, for example, we're seeing displacement because that's active. We're seeing some other functions. But the main point that I'm trying to make here is that you would have errors because essentially the load and the modeling based on your approach, loads have not been fully transferred, right? And we have also shunted some processes as we went through this. So how can we begin to address some of this, right? I will exit this point right now and then come back to the model. First of all, there was a very critical step that we're supposed to perform that we did not perform. I'll show you that. So if we go to the story plan view for story 1, let's take a look at the plan view. And on that plan view, there are about 4. We have, like, say, just referencing these 4 types of slab here. There's another slab here. But if you look at the properties of this slab, for example, let's take a look at this slab. We still have this slab specified as a type 1, which says it is supported on all 4 sides, but it is continuous on all 4 sides rather. But technically, that's not the case, as you can see, right? So a good thing to first of all do is that, irrespective of whether or not you're having, especially when you're having slant members, you want to ensure that you set the slab types to the correct type, either manually at the point of placing them, or you can set it, you can ask the software to automatically define these types for you based on the continuity of the supporting edge, right? So in this case, now we're saying the minimum edge coverage length ratio for a site to be continuous is that slab must have a support that covers 70% of the span, right? So let's click on OK, and you can see the types of slab that have been specified right here. So these have been computed. So these are no longer type 1 slab as we had earlier. So this is one good step to at least begin to realign your model appropriately. Then let us look at what we have here. So if you look at this beam right here, you see that this beam is being treated as a cantilever, even though it is supported, right? You see that cantilever mark there. You also see this cantilever mark here. So you can see that this is quite kind of because of the plane definition that we've changed. Now we are seeing that some errors are obviously in the line because these beams are not showing supported, even though they're actually supported. It's now trying to treat them as a cantilever beam, which is, of course, again, is an error coming up. And this means that you need to closely take a look again at the model that you created, right? And so you can go back to such a member and you can redefine the ends of those of that beam. So you can decide that, look, this is not cantilever, both ends are supported, right? And you can see that has now been updated for this beam right here. And then we can do the same for this to say that both ends are supported and it is not a cantilever. It's not a cantilever beam, right? So both ends supported, and you can see that that cantilever marker has gone off. Now, why are we having to do this? This is just to let you know that you would need to pay more attention once you begin to create inclined members. I think this is a very important knowledge to take home from this webinar. That once you begin to play around with the 3D geometries of your member, depending on your model, you will then need to take a closer look compared to when you are modeling regular members that do not have any kind of inclination in them, right? Then if we go back to the analysis section, just again to further demonstrate what is happening here. If I go down to the footings, right? If I go down to these footings, at the footings section, sorry, can you hear me, please? Can anyone hear me?
Yes, sir. You are audible, sir.
Oh, okay. Thanks, Alex. I got your message. Sorry. All right. So I'll just run a quick analysis to try to just again wrap up this what we've shared so far. Maybe on another session we can have something maybe more deeper than this. But again, so I'll do a quick analysis, right? And then this time around for the analysis section, under the model options for the slab, I will include the slab in the building model. And so I will request that the story be meshed. And I would also like to have the decomposed slab loads in the mesh stories. So I'll tick that. And then the difference between this and what we did earlier is that in this particular case, we'll be able to generate a mesh as part of the design process. And that will also help with the proper analysis, right? So if we go back then and then we selected, if we go back then and we are okay with whatever parameters that we have, they have not made any changes anyway. And so we'll go back to the analysis. We could then carry out the building analysis and okay, so now if we go to the analytical model now, this time around, we can then see sorry, it seems I skipped something. Sorry about that. Okay, just a quick one. Go back to. So what I'm trying to demonstrate at this point is just to let you know that you can definitely request that you have your stories meshed. Sorry, I didn't check this earlier. You can mesh your stories and include them in the analysis process. And so when you have slant members and you have members that are probably not directly supported by a structural member, what you can do is that you can have those included, you can have those slabs meshed, and based on that finite element analysis that will be carried out, your loads are properly transferred and you have a more accurate model, right? So I'll just quickly run through this again to demonstrate that point. Please, are there any questions so far?
No, sir, we do not have any new questions here.
Yes, I observed, I just took note that I'm taking quite long on the session. And so apologies for that. I wasn't sure of how long I had. And so sorry for that. So, but just to close out on this thought at this point, okay, so back to the point I was trying to make earlier, right? Is another take home for you is that whenever you are carrying out any slanting member, if you have any slanting members in your model, in such a way that you don't have very accurate transfer of load, for example, through finite through yield line method, it's very important that you use finite element analysis, right? So this is another take home from this webinar, so that you know that your loads, for example, this particular beam that we see here, does not provide a support does not provide any major support to this slab right here. So let me just turn that a little bit. So we can see how this beam has been slanted, and then we can see how this slab also is existing. So this slab is not enjoying a lot of support from here, but on the plan view, you see that the yield line method wrongly distributes that load. However, with the finite element method, you can be sure to properly capture some of these loads better. So in summary, for this webinar, a few key highlights, a few highlights of what we've been able to cover. First is that Protastructure as a tool gives you that flexibility needed to be able to create diverse forms of complex structural members, whether it is slanting vertical members or inclined vertical members or inclined horizontal members. Secondly, the tool also allows you to be able to have good control over how these members have been created. So you are able to easily modify, you're able to reorientate, you're able to change certain aspects and correct the model flexibly, also in a 3D view environment with a lot of ease. Thirdly, is that you are able to immediately see, for example, by building model checks, you can easily see if you have errors in your model based on how you created those models. And again, this is a very, very important tool. And then fourthly is that during the analysis, of course, you have options that allows you to cater for loads accurately. In our case, what we have done is that we have randomly generated a very simple model just to demonstrate some of these points. But in real life scenarios, you could have very troublesome or complex geometries where you would have slant members that you may not be able to properly model without slants. And if you're going to be able to do that, you need to be on top of your game. So you have tools that also allows you to properly model and analyze and be able to get a better result out of that. Thank you.
So we also have a question. We got a question. What is eigenvalue analysis?
Okay, so I won't want to go through. I won't want to go too deep into that. But if I go back to just to not spend too much time on that, if I go back to the analysis, so there are quite a number of analyses that Protastructure allows you to be able to carry out, right? Eigenvalue analysis is one of them. The ones that we are very conversant with is the, maybe I should start with that. The ones that we're very conversant with is the static analysis, where we know that we don't expect the entire building to be in motion. And so each of these members are designed in such a way that they are able to, we assume or we take cognizance of the fact that the building itself is not in motion, or that it's not exactly distorted, right, by virtue of motion or any kind of instability, major instability. However, eigenvalue analysis has to do with eigenvectors. It's quite technical, right? Has to do with eigenvectors, which relates to linear algebra. and it's simply just a method of carrying out a design based on linear transformations, right? So it's a method of carrying out a design, but at the same time, you would need to be very certain of your methods of analysis before you utilize them, right? So what you want to do is to be sure that, for example, if you want to use this tool, you understand the outcomes, and then that you also understand the exact scenarios that you need to use them. I think I need to touch on the fact that Protastructure allows you to carry out multiple kinds of analysis, pushover analysis, eigenvalue, of course, static analysis. You can also have analysis that also helps you out in situations where you have you're trying to design for earthquakes, right? So all these possibilities are quite available in Prota. Maybe in a separate webinar when we are looking maybe specifically at some of these areas, we can touch on them and look deeper at them.
So we'd like to take one more question. That was why sometimes product structure gives much reinforcement in the upper column and lower reinforcement in lower column, which is not logical as the lower column is more loaded.
Okay, yeah, so this is a very good question. We get a lot of this type of questions in Nigeria as well. So to respond to this question, let's quickly get to the foundation level so that I make my response very practical, right? And I'll also show you something quickly. So let's switch over to the plan view at this point. Let's take a look at the plan view. Sorry, use plan view. Okay, let me close this for now. Now, what I want to do quickly is that I want to show you the forces that are transferred from these structural members, right? We'll look at what is transferred from the roof level to the first floor, and then what is transferred from the first floor to the foundation, right? So right now we're on the story 1 level. Let us go to the review and go to visual interrogation. And under that, let us take a look at the column display. And for this, let us try to display, of course, the transfer column, but this time around, I'm interested in seeing the axial load, the bending moment, and the shear force that are transferred based on, let's say, the G plus Q load combination, right? So I'll click on OK. It will show this at the bottom of each of these columns, and I'll click on OK. Now, what this allows me to do is that, for example, for this column B1 right here, I can see that from the column above, a load of 215.8 kilonewton is transferred. Now let's see the moments at the direction 1 and direction 2, right? So the governing moments, right, for X and Y direction is 6.1 kilonewton meter and minus 7.8 kilonewton meter, right? We can also see the shear force there. Now for this same column, let us quickly go to the foundation level. So now we see the moment that is also transferred to the foundation, albeit not as large. This has not changed so much. But to go back to your question, right? Protastructure does not. If I reference your question says that why do we have the columns below usually having, sorry, the columns above sometimes having more reinforcements than the columns below, right? Because technically the column below should be carrying more load. Now, this is very true with respect to axial load, right? So for example, for this column, for the axial load, which is the N load here, I expect this value to be larger than the load that is coming to it above, which is very reasonable, right? So if I go to the story 2 right here, I can see that the load going to the first floor is only 57 kilonewtons, right? This is very reasonable and understandable because, I mean, this is just the roof load and all that, but see the moment transferred at this point. Can you see that? The moment transferred here is 2.7, right, and minus 16. Can you see that? So what I'm trying to let you know now is that Protastructure does not design for your axial loads alone. So your point of argument is correct because it is partially true for the axial loads. The axial loads will always increase floor to floor from top to bottom. That is very correct. But for the moments at an upper level, depending on your connectivity, the column may be subjected to a greater moment, bending moment, right, than at the lower level. So for this, at this story level here, at the top level here, you can see that we have a bending moment, right, that is up to minus 16 kilonewton meter. But at the first floor level, you see that that is lesser. It's simply because of factors like framing, bracing, and what else have you, right? The span as well. Okay. So in instances where you have very large moments at the upper columns, you will discover that in order to be able to design those columns to resist the moment that they are supporting, they may need more reinforcements at that point. This is usually the primary reason why you have columns at the upper level having more reinforcement or higher reinforcement than columns at the lower level. Whenever you have that kind of scenario, I will task you that you should try to review your model, check your model. You discover that the moment that the column at the upper level is supporting or resisting is significantly higher than that which the bottom column is resisting. So the higher reinforcement you see there is not for axial load, is not to provide for axial load, is to provide against bending, right? It's to provide against bending. And that is why those reinforcements would most likely be higher. Yeah. I hope I responded to your question.
Yes, sir. So I think we
yeah.
are also running out of time. So I'd like to request to all the attendees, in case you have any further doubts or you would like to have any deeper explanations, please refer to our websites and you can go through our training packages and you can learn about all the softwares, and you'll have so much more to be offered there, and all the queries will be answered thereby. And now,
sorry, Sasha, just one more point from my end. I would also like to please let the participants know, if for any reason whatsoever you maybe have further questions after this webinar, maybe you watch the video recording and you have some more questions, please, I will be available. You can reach out to Inziza Global, and I'm sure that they'll be able to communicate your questions or any inquiries you may have to me, and I'll be very glad to support. One thing I also know is that I know that Inziza is also very available and willing to provide support to all their trainees and participants. And so I can let you know that if peradventure in any areas, for example, on a real life project that you may have, you may need some extra support, you may need to maybe have some inquiries into maybe why you're getting certain results. Of course, you can again reach out to Ziza. I'm always available, and I'll be very, very happy to support as required. Thank you.
Thank you so much, sir. And I'd like now to give the screen to Mr. Eddie Robert, our training sales executive, and he would like to have some words. So please, Eddie, you can take the screen.
Thank you, Session, and everyone who participated in this webinar. We are so glad to have you around here, and I'm not intending to take any more time with you. I just want to share a quick update with you. So if you can see within the chat, I just shared with you the link to our platform where these courses are actually now prepared in their full capacity. And I just wanted to drop one announcement for you who just attended the webinar to let you know that we have decided to offer you with a 50% discount to the course, because we have the full prepared course for the RC structure engineering with the Protastructure. Just in case you had more questions regarding how to use a Protastructure to deliver more world-class projects, this is what we do 24 hours, 7 days a week. Yeah. So would love to invite you guys in case you are interested in taking the full course into the structural engineering. the course is well prepared. We have certificates directly from Turkey, where the Protastructure operates from. We also provide you with the license in case you have just started the courses. And we are also assigning you with the technical support person. Because you're taking your courses online, we want you to be in touch with the person so that they can support you anytime you have any question regarding on the progress and everything you're doing. So that includes in the package. So you get 3 months access to the course. You get a technical support person who will assist you on the journey until you master the art of delivering good projects with strong structural understanding. We give you the software and its license to help you exercise the project and going forward. We also assist you in delivering the project so that we can validate if what you learned, you understand on a deeper level, and we'll give you the certificate from the headquarters of the software. So we have a number of students taking the courses now, and we'll be glad to have some of you joining us. So you can take a look from the link I just sent you in the meeting chat so that you can explore more on this course. And yeah, if there is any question, we will be happy to take it. And yes, I emphasize that it's normally $800 to take on the course, but this time around, we're putting the cost to $400 for you guys, because that's the least we can do if you decided to join us today. Yes, if there is any question regarding that, I'm happy to take it. Yes, thank you.
Thank you
Any
so
questions?
much. So please, if there's any question, please put it up. So there's one question, do we need to pay today or just book the seat?
It's preferably, of course, preferably if you can pay right away, it helps. But if you can also reserve to pay sometime later, you reach out and we can make that work. So everything on the platform is available. If you have your card with you, you can just pay with your card on the platform, and then we give you everything with your email, and we set up your account and everything. So yeah, you reach out to us and we'll be glad to assist you on that. If you want to book it for later, we'll make it work as well.
All right, thank you. Do we have any further questions that needs to be answered?
Yes, Teogene, can you explain me the amount you can pay when I join you? Yes, normally you would pay $800 to join the course, but then there is a discount that applies of 50%. So you'll be paying now only $400 to join this course. Yeah.
And there's a question about what are the timings of the course and what is its duration?
Normally, the course, we give you access of 3 months to the course because we expect you to be done within 3 months of including the learning and delivery of project. So within that 3 months, but then if needs be for some particular occasions, we're flexible to extend the duration by a certain period of days to help you finish the course of work. But yeah, 3 months, that's the access we give you.